Hi kids, and welcome to the Magic Show. In this magic trick I am going to show you how you can combine RSA cryptography with AES cryptography. Before you start playing around with it, realize though that first of all you're going to need version 8.6.4 of Magic to reproduce what I am doing in this video. And also there's a link in the description of this YouTube video to this page where you can find the code that I'm using. It is the cryptography tutorial page in the documentation for Magic. So anyway, with that out of the way, what's actually occurring here is that first I'm creating two key pairs. RSA key pairs. Now one is intended to be the recipient's key and the other is intended to be the sender's key. Then I have some message here I want to encrypt. However, I don't only want to encrypt it, I also want to cryptographically sign it. So what I'm doing, I'm encrypting the message with the recipient's public key. Then I am signing the message with my own private key. And then I am passing in as the signing key a fingerprint. I'm passing in the fingerprint, which is basically the SHA-256 value of my own public key. This allows the recipient to look up my public key from the fingerprint and then verify the integrity of the message. Then just for simplicity I am decrypting the same message. After the message has been decrypted, I still don't completely have access to the raw message, or rather I do, but the message is also concatenated with the signature and the signing key fingerprint. So it's still kind of raw data, you might say. So afterwards I need to verify the integrity of the message, which basically verifies that the message is cryptographically signed, it has not been tampered with. And this I do with the sender's public key. Or yes, the sender's public key. So basically I take one message, I encrypt it with the recipient's public key, I sign it with my private key, then I send it. The recipient decrypts the message with his private key, and then he verifies the cryptographic signature with my public key. And this ensures that the message cannot be tampered with, it cannot be read, and the message originated from me. So let's evaluate it. And the end result, of course, is that I have access to the exact same message as I started out with up here. So that is combination cryptography. What actually occurs here is that this message here, some super secret message, which can be anything, it can be a file, it can be an email, whatever. It is first cryptographically signed and then it is encrypted, resulting in that the only thing that's actually communicated in plain text in my encrypted message is the encryption key I used to encrypt the message. This is necessary such that the recipient can look up his private key to decrypt it. After the message has been decrypted, he has access to who cryptographically signed the message, who sent the message, who did it originate from. And then he can verify that the message was not tampered with, giving him cryptographic guarantees of that only the owner of the private key that is associated with the public key he uses to verify the message was the person creating the message. Now, so how can we use this? Well, I have another little snippet here. If you click the load button and you filter on Magic and you choose magic.crypto.http.eval. This snippet is really cool. However, before you can do it, you need to set up cryptography in Magic. If you haven't done this already, you need to click the crypto menu item here. Then you need to select the key strength. For simplicity, I'm just going to choose 2048. And then you need to manually type a seed, which is basically a seed for the cryptographically secure random number generator. And then you click generate new key pair. My server now has a key pair, an RSA asymmetric key pair. This is my public key, my server's public key. And this is my server's public key's fingerprint. This is the identification of my key pair, you might say. Now I can copy this, and of course I'm gonna have to do this localhost, basically loop back into myself, because I only have one Magic server, which is localhost. However, what I'm going to do here now is that I'm going to create a quote-unquote friend by importing my own keys. I'm going to befriend myself here though, but normally you'd have access to somebody else's public key in this part of the video. Click import, I paste in the public key, and now you see the same fingerprint. Then I give this instance a name, Thomas Hansen II, localhost, colon, 55247, I think. And then I can give him an email address. And then I can associate a bunch of execution rights with this particular public key. And these execution rights are basically what I want the owner of the private key to be allowed to do on my server. So I want him to do log.info, I want him to do return. Okay, those are probably the 5 things I want him to do. Then I click OK. And for those having seen my previous video about this, I'm a bit sorry, but I've changed the way this works now with some advice from a bunch of cryptography experts over at Reddit. So that's why I am creating this video now. Now I can go back to the evaluator, then I can click load, then I can filter on Magic, can load this snippet, and I can evaluate it. And actually, what happened here now is pretty cool. Because this slot invocation here takes 2 arguments. It takes a URL argument and it takes a Lambda argument. The URL, of course, is the URL to where I want to transmit my payload. The Lambda argument, however, is a piece of hyper-Lambda code, and it could be anything. I could send hundreds and thousands of lines of hyper-Lambda code here now if I wanted to. This particular Lambda does one simple thing, it just invokes log.info. And actually now we can go into our logs and we can verify that it was successfully executed. And it was. Here you can see how the world. So basically this piece of hyper-Lambda was sent from one client to another server, who happens to be, of course, the same server as the client, but it's irrelevant. It would have functioned perfectly if I had 2 different setups. This hyper-Lambda is sent from this website as a client, then it is transmitted to a server. The server actually executes my hyper-Lambda and then returns whatever I want it to return, which by default is success. If I want to return something else, then I can do return colon Thomas Hansen is cool. And now you see it returned what I wanted it to return. I can also have it return nodes, etc. Now you see it returns the hyper-Lambda as text back to me, at which point, of course, I can easily parse the hyper-Lambda. Now, this allows me to create a cryptographic secure execution context, kind of like signed AWS Lambda invocations, except the signatures here goes both ways. So not only do I cryptographically sign my payload, which gives the server guarantees of that the payload originated from me, but also the server cryptographically signs its response object, which means that when it comes back to me, the client that executes this HTTP invocation, then the client has guarantees of that the response originated from the server. And the by far coolest thing here is that I now, in my crypto menu item here, if I click it and I click this particular instance, which is the public key that is used to verify the cryptographic signature of the message I originally transmitted from the client, is associated with a bunch of keywords or slots. So these 5 slots here now becomes the keywords I can legally invoke on this server. If I now go back here, for instance, to the evaluator and I load the snippet again, and I exchange log.info with log.error, which is not whitelisted, right? Then boom. Invocation to cryptographically secured HTTP REST endpoint was not successful. Then I can go into my logs and I can actually see fairly good why. Okay, slot.error doesn't exist in current scope. Then it logs access denied because it denies access. Then it logs the result of my HTTP invocation here. Of course, parts of this would be logged on the server and parts of it would be logged on the client, but the client and the server is the same here now. If I now go to the crypto menu item, I click my entry here, I add log.error, I save it, I go back to the evaluator, I load the same snippet again, and I exchange log.info with log.error, and I evaluate, everything is kosher. HTTP status response of 200 headers and success. And that's it. Yet again, there's a link in the description to this article. In the description of this YouTube video, you can find a link to this article where you can copy parts of the code I was using. The rest of the code you can find by simply clicking load and filtering on magic and choosing magic.crypto.htp.eval. Thank you for watching. Have a nice day.